I asked you yesterday to try and plot this parametric equation, see what it produces, and it should produce something you are familiar with. This is actually a parametric equation for a circle. You may know the general equation for a circle is in Cartesian form is x squared plus y squared equals r squared, which is really Pythagoras theorem. All of what we're talking about is Pythagoras triangles inside to create this endpoint, all of them with the same length. Now, one thing we've got to do is find out ways of actually creating Cartesian equations with these. And what we need to be able to do is create all our trigonometric identities and spot them quickly. And so we need the trigonometric identities to be able to do this. Remembrance you've got to do is quickly look at what's relevant and remember what all the trig identities are. I'm just going to put them in here now. They're things you need to actually recognise and be able to work out where they come from. Okay, so they're the main trig identities we need to be able to work with these to form Cartesian equations. Now, it doesn't necessarily look obvious, apart from if you look at the first one and what we know as the Cartesian equation. What we can produce quite quickly is realising that if I replace my cos A here with cos t, and then replace that with the x, I get x squared. Sin t replaces the sine squared a, and we actually use that identity to give us our Cartesian equation. So that one actually goes sine squared t is y squared, cos squared t is x squared, and using that identity we get y squared plus x squared is equal to 1. Now, there's a weirdness that happens with these as well, that if I did ask you to have a look, and what happens if we start moving things around, and you'll notice there's something odd with what happens when I add in the x direction. Normally when we add in the x direction, the graph moves backwards. So if you remember, if you put in here y squared plus x plus 1 squared equals 1, that actually moves your circle backwards 1 square. But what happens in the Cartesian one is, because of all this rearranging we're doing, this actually rearranges out to moving the equation the other way around. So if I now put this back into my Cartesian form, so this is sine t squared, and all of that is cos squared t. I get cos of t is equal to x plus 1. And hopefully you'll realise now that if I do the subtract to get this, what is happening to x, hopefully now you'll see what happened, why this moves it backwards. So we move in the x direction backwards. The adding a number one in the y one, it's already put that on the opposite side to the y, which is why that doesn't flip. Okay. A couple of other quick things with this. You can multiply them, and let's do the equation of a multiplication one. So let's do y, and I'm going to flip this round, and there's a reason for that. This time I'm going to do sine t, and y equals 2 cos t, and see the effect of this. Again, we're going to say that t is in the range of 0 to 2 pi. And I'm going to do a little bit of an odd thing first. I'm just going to find the domain and range. So the domain is when we find out when x is maximum. And this is the logic they use in the formula ones. You can do it by differentiating x with respect to t, make it equal to 0 and find out what values of t are important. But the max sine t is 1 when t is pi over 2. Unit circle, cos, sine. So when pi over 2 for t, we get our maximum. And we get x is a minimum. At the other end, when sine t equals minus 1, which is when t equals minus pi over 2, or sorry, 3 pi over 2, because we're going 3 ways round to keep it in that range. To look at the range, we want y max, if possible. And the y max of 2 cos t is when's t maximum? Is when t equals 0. So when the value of t is equal to 0 is when cosine is the max. So that leads to y max, y at 0 is 2 times 1, which is 2. And when we do t equals at the other end, which is pi, gives me the other limit, y of pi is minus 1 times 2. This is minus 2. So this actually gives me a function in the y direction with a range of minus 2 to 2, and in the x direction a domain of minus 1 to 1. And what it actually produces is an ellipse. Now if we do the turn it into a Cartesian equation by doing the same trick, we now need to say we're going to use sine squared a plus cos squared a is equal to 1. So rearrange this equation without rearranging it really. We know that sine t equals x, and we know that cos t is y over 2. Replace those in here and we get x squared plus y squared over 2 squared is equal to 1. And that's the equation for that ellipse. So what we actually have here, if you recognise this 2 comes from the y direction and the x direction is the bit over on the other side, that leads to a general equation for an ellipse. And the general equation for an ellipse has a form where that is a, that distance is b, and they're the denominators for the x and the y direction. So x over a all squared plus y over b all squared equals 1. Not the radius, because these are the 2 radii. And this is the sort of thing you have to be able to use to be able to actually work out the distance around an ellipse. You can calculate the area. The area is pi times a times b. But you have to actually be able to turn an ellipse into a Cartesian equation if you want to work out the perimeter. Okay? Not going to say circumference for this. One last little beauty with these is, like we showed before, if you want to move this in space, you can just add the vector onto it. It's effectively the same, and I wonder if this is going to work, as adding the centre point, 2, 3. So that gives me, if I actually add these 2 vectors together, the 2 goes into the plus sign, and the 3 goes on the outside. And that gives me the same ellipse as I had before. So that's an introduction to using trig identities as parametric equations.